Hello, everyone. My name is Arup, and this is Isaac. We work for Ooyala, and what we're going to talk today is how you run a Spark streaming on top of Yarn in production environment. Uh, just a little bit about Ooyala. So, we are a video platforms company. We were founded in 2007. We have 300 plus employees worldwide, and we have around 200 million global users. And we work with a lot of broadcasters and media companies. Yeah, just to tell a little bit about our team. So we mostly work in the ETL part of our data processing pipeline. So what we do is that we ingest around 5 billion events per day, and it consists of decoding event that we get from our people who are watching video on our platform. We enrich that and we process that in the permanent storage, and that's sort of our ETL pipeline. By analytics data, what we are interested in is like number of plays, displays, conversion rate, geo information like which country, which state users are viewing videos, the device information, is it Android, iPhone, desktop, number of unique viewers, in engagement, it's like which part of the video is popular. So all of this analytics data is very important to our clients because they make business decision based on this analytics information. The aim of the pipeline is that it should be running 24/7, very like low latency, and we try to have as less data loss as possible. And of course, we don't want any human intervention. We want it to be running all the time, right? Again, this is not the whole data pipeline architecture. This is just the ingestion pipeline. So what we have is we have HTTP receivers. This is our Nginx servers, which actually receives events from users whenever they are using playing videos, be it on browser, on Android, iOS phone, etc., etc. And we use Apache Kafka for distributed messaging, and it gets processed on top of Spark. We use Spark streaming, and we run it on top of Yarn. And finally, we put it on HDFS, and that's where the other pipeline, downstream pipelines, pick it up from. We're going to discuss a few issues we had faced. But just I want to set the stage correctly that yeah, we have had few issues with Spark streaming, but of course there are a lot of flexibilities we have in Spark streaming which are not available in other frameworks, like reuse of code in streaming and batch, and we'll talk more about that later. And whatever issues we are going to discuss, they are not huge. We have workaround for that. For some of them, we have submitted patch in Spark itself, and for some other we have sample codes which we would soon open source, but it's available as of now as well. We're going to share the link at the end of the presentation, and of course we're going to talk all the different, what are the things we need to be aware of while running Spark streaming on top of Yarn. Okay, so processing, there's two ways of doing it, right? It's like we could do batch as well as we could do streaming, right? The advantage of batch is that the notion of reprocessing is well defined. You have like certain defined input, and you want that it's going to produce some output, and it's easy to reprocess if anything fails in doing a batch processing, right? Which is not very trivial in streaming because data is always coming. There's no notion of start and end. And while doing batch, you could make aggregation on historical data. You have more context than in a streaming environment, right? And of course, consistency is easier to guarantee in case of batch processing. Now, while coming to streaming, right? If you want something real time, you have to go for streaming, right? Batch is always delayed. So if you have a real time requirement, the batch is not going to solve the problem. You have to go for a streaming approach, right? And the streaming doesn't have the scheduling overhead that is present in case of batch. So that's one advantage of streaming. So why Spark and no other streaming platform, right? So one advantage of Spark is that it's one code base to maintain and test, right? I mean, you could run code and run it as Spark streaming application, or you could run it as batch application, right? So it's always good to have just one code base to maintain. So that we see as one of the major advantages of using Spark streaming, because like if you go Spark streaming and Hadoop MR, we'd have to maintain two code base, and Spark enables us to have just one code base. We were running Storm earlier, but we had few issues with Storm. So Spark, we sort of have developed some in-house expertise as well. So we feel more comfortable with Spark. So it was an easy call for us to go for Spark streaming. And it integrates out of the box with Yarn, and Sandy described a lot how Yarn and Spark play well together, and just having to manage one cluster works really well for us, right? I mean, we just want to have one resource manager, that is Yarn. We could run either Hadoop MapReduce, Spark Batch, or Spark streaming on just one cluster. So I'll hand it over to Isaac, who's going to talk more about the best practices.
Okay. So next question is, why do we use Yarn? So we actually tried using Spark standalone cluster at some point. Our main problem was that our infrastructure people in Ooyala are experts in Hadoop and experts in Yarn. They didn't know much about Spark, so we had to maintain the cluster ourselves. Having to maintain the cluster and maintain the application at the same time is really a time drain. Yarn allows us to use the hardware better. Upgrading the version in Spark is trivial. In Spark, you actually have to, if you use Spark standalone, you have to redeploy the entire cluster. In Yarn, it's just you just change the dependencies. You can be running two different versions of Spark at the same time in the same cluster. And well, and of course, they're having years of expertise using Hadoop and Yarn, so all of that can be leveraged. On the other hand, there are some pitfalls to Yarn. One of them, it's a 384 MB overhead per container that Spark imposes. This means that small containers are not feasible. Probably you don't want to have any container less than 2 gigs. It might not be bad, but you need to be aware of that. Spark has a UI, Yarn has a UI. They are completely disconnected from each other. This has a lot of effect on the logs. We'll talk a bit about later, and the previous talk mentioned it. And also the Yarn class path is automatically added to Spark whenever you run an application. The Yarn class path can be huge, and it can cause conflicts. We've had conflicts with Pig, we've had conflicts with Log4j, so you need to solve some of those issues. So these are the issues and solutions that we're going to talk about in this presentation. Launching instrumentation, consuming the data, logging, and actually writing out the outputs. So launching Yarn, this is how you could launch in Spark 0.9. In Spark 1.0, there's an easier way of launching using just a shell script. We're not going to talk about that. It's pretty much the same, just inside of a script. It's the exact same application that you could launch in a Spark cluster. You just have to use a slightly different command. So you have to export the location of your Spark jar, and your Java command needs to include the Hadoop configuration, the application jar, and the Spark jar in the class path. You will use this yarn.client class, and well, you can add additional jars. You can say which class to run. You can pass one or more arguments that will be passed to your application, and you can give your application a name. Besides this, you can specify how many nodes you want, how many containers you want, the memory per container, and so on. What this will do, it was mentioned before, it will launch application in Yarn. It will like an application master, and the application master will launch all of the workers, and it will actually track the application until it is done. So it will print a report every second, and it will exit at the end. This is not great for streaming. You probably want an application to be running for a few weeks at a time, and the client is probably going to crash before that. Then how do you track it remotely? We actually modified this slightly. We wrote a streaming client. It's very similar to what the other one does. Difference is that before launching the application, it actually checks the cluster to see whether the application is running already. If it is running, then it just connects to that application, monitors that application, and exits whenever that application finishes. If the application didn't exist, then it launches the application as usual. This allows us to keep track of the application after 2 weeks, a month, however long it is running. And this also allows us to be able to relaunch the application easily by using an upstart script. So the upstart script just is connected to the client, and whenever the application crashes, the client will crash and upstart will relaunch it. If the client crashes alone, then it will be relaunched, but no new application will appear in Yarn. Again, all of these codes are in a public gist that we will give you the address at the end. I'm sure all of you have seen this screen. There's nothing too different. You can, in the list of executors, you can actually see the location of each of the executors within the Yarn cluster. It will be useful and for finding logs. And in the Spark stages, if you're running streaming, you'll see one or more stages that they get repeated for every batch. Spark 1.0 also includes this new tab, streaming, where you can actually see your receivers, whether it's Kafka or HTTP, see how many records you've read in the last batch, and so on. Let's talk about the main failure cases that we've seen in streaming in Yarn. So with respect to streaming, the consumers and the actual processing are completely independent. What that means is that the task could stop and the consumer could keep consuming, or the consumers could stop consuming and the task will continue. And both of these are bad. In one of them, you're losing data. In the other, I mean, if you have a buffer, the data is building up in the buffer, but you're just wasting resources. Also, if you're consuming data too fast, you can run out of memory. And we actually have a solution for this. We'll talk about it in a bit. So the first way to solve these issues is to actually know when these issues are happening. For that, we use some instrumentation. So this is the way that you could implement instrumentation according to the documentation, which is not very clear in the first place, but you create a source, you register that source, in this case, the number of requests. This is not very clean. This will just give you metrics about the driver. You probably want to also know metrics about the workers. To do that, we actually use accumulators. So we implemented a Spark instrumentation class. You can find the code at the end. In this case, we create a Spark instrumentation. We create an accumulator. We register this accumulator with instrumentation, and then we register the instrumentation with Spark. What this will do is it will create a gauge and a meter with that accumulator, so we can get a sneak peek into what is going on in the entire cluster. If you wanted to be fancy, that accumulator can actually keep a different record for each worker in the cluster. You may also want custom sinks. Again, the documentation is not very good at how to write them. This is a custom sink for Datadog, which is what we use. You can give any properties you want. You register your reporter, and you're done. You can look at this later. And this is an example of the metrics that we can get from this. So we can see the processing rate. We can see a number of jobs running. We can track the memory remaining in the cluster and see when the application might be down, and get numbers on the record, on our processing rate and the total number of records. In this case, we actually have a daily accumulator, so it will reset at the end of every day, which is good for something that will be running for a few weeks. About consuming data, this is the way that the documentation will tell you to consume data. I assume most of you have seen it. Let's not go through the details. The issue with this is, well, first, if you follow what the documentation says, all of the consumers will show up in the same node. You will have bandwidth issues probably. There will be a limit on how fast you can consume in a single node. It's bad. On the other hand, if your consumption is too fast, then as we mentioned before, you might have out of memory in the nodes that are actually running the tasks. The consumer will not know if any tasks are actually happening and will keep consuming and potentially losing data. And as of Spark 1.0, if you launch a receiver in every node, that will actually block the node from doing any other work. We're trying to solve that. We have a hack right now in our production application to address this. So this is the way that, according to us, you should actually consume your data. So we actually have a pull request with Spark for throttling the consumption of data, which is the second line in here. So you can say how much each receiver can consume per second. Other than that, if you look at the Kafka inputs block, you actually want to create a different stream for each partition and then union them at the end. You might do the same for HTTP. I mean, in our case with Kafka, the worst thing that happens is that we need to go and figure out which offsets were lost. If you had an HTTP receiver and you could not consume fast enough, then that's data lost completely. Even then, there's data loss sometimes. Like the streaming data is replicated, so that's not much of a problem. But if your application crashes, you can lose up to one batch of data. If the tasks are hanging, you lose the data that is being consumed. And Kafka makes the fact that there's auto-commit in Kafka makes it hard to recover this data. We can address this by disabling auto-commit and keeping track of the offsets. We're still looking into this. Now.
Okay, Sandy spoke a lot about how to find logs. So all the logs are available in HDFS for completed jobs. So for all jobs, you can either use the Yarn CLI or you can always browse the HDFS to find logs. And logs of running jobs are available in the Yarn UI, but it's not super easy to find. The way to find it is that first you'll go to application in the Yarn UI, then jump onto a Spark UI, figure out what are the executors, and go to Yarn Resource Manager, find those nodes, and go to the running application for each of those nodes, and then that's where you find the log. So it's not super easy to find that. So ideally, hope in future Spark UI would directly link to the logs which are available on Yarn nodes. If you want to customize how you want to log, Spark has an environment variable called Spark log4j-conf. It makes it easy to supply your own custom log4j configuration. But as of now, whatever be the file name, it would always map it into log4j.properties and make it available to the application. And with a huge class part like Yarn, the problem is that there could be multiple log4j.properties file, and so you wouldn't know which one got picked. So we have filed a Spark Jira so that it also retain your name. So you could name it in such a way that there's only one copy available in the class part, and that gets used. With logging, the thing is if you have too much logging, it slows down your application, and again, slows down the application. It's very hard to figure out where the issue is, and also you don't want too less log. You want the good balance of log. So we saw that in our application, certain Spark classes are there when they're even in info level, they log a lot. So we recommend that you set the log level for this particular classes to 1 and also set the additivity to true. That way the logs are manageable and it's easier to find where the issues are. Now coming to streaming output, Spark and Spark Streaming, they already support natively writing in Hadoop. But in our experience, when we wanted finer control, we preferred using for each RDD and map partitions. It lets us give us finer control how we want the output. And as in our pipeline, we use Parquet files. The advantage of Parquet files is that it's columnar binary format. It's written in type safe, meaning that ints would go as int and not a string that you need to parse back. And it out of the box, it integrates with Hive, Shark, and plays well with the rest of Hadoop ecosystem. So we have been using Parquet and would highly recommend using that. Coming to conclusion, so one thing is that if you have real-time, if you have a low latency requirement, you need to have real-time pipeline. There's no alternative to that. But sometimes in real-time pipeline, message drop, process crashing, and where do you resume? It's the notion of reprocessing is a bit hard when you use real-time pipeline. What we have opted for is that we have a real-time pipeline which makes data available with a very low latency, but we do have a batch job running following our real-time, which would correct all the errors that we see in real-time. So the hybrid model of real-time and batch gives the best of both the worlds. You get low latency as well as you get the correctness of batch. As Isaac mentioned a lot about instrumentation, for a real-time pipeline, instrumentation is super important. You want good visibility of what's going on in a cluster. So you should definitely instrument your code very well and monitor those instrumentation to see the status of your real-time pipeline. So instrumentation is key to a healthy real-time pipeline. And logging, we at least saw that you need to tune the logging levels. That way logs are more manageable, and yeah, you could find issues easily. So that's all from our side. So if you have any question, ask now based on time, and feel free to email us. And we're soon going to open source all the code samples that we have mentioned. Either is some of these are already available as patch to Spark. Others will open source on the Ooyala repo, and till then, some of the skeleton code is available in the link mentioned here. Cool. So, yeah, we could take few questions. Yeah, so the question is, are we using Parquet file format as the output of streaming? Yeah, we are doing that now. We had used Cassandra earlier, but somehow it was not playing well with our downstream pipeline. And but we do have merge jobs which would merge the Parquet files. So that way we solve the small file problem. But HDFS sort of, we have got good performance with HDFS, so that has worked well for us. Not 5 seconds. We run a batch of window of 30 seconds. 1 minute now. 1 minute. Yeah.
What kind of latency are you able to do, and what was your longest streaming job?
So our latency right now, our batch is 1 minute, so our latency may be 1 minute and 20 seconds. We have run a job for 3 weeks without it crashing. Yes.
Yeah, but a lot of it has to do with, I think, the Parquet file, writing Parquet files as well. So that seems to be memory heavy, so we are trying to figure out how to optimize that part. But a lot of our memory issue has been with the way we are writing Parquet files.
What's the size of your cluster, and did you hit any scalability issues?
So scalability, we haven't faced any issue. I think that has to go with the fact that we are using Yarn. So we have a big Yarn cluster, and based on how we want to scale up, right? We just, while launching our streaming application, we could tell how many containers we want. So it's been working fine for us.
How many nodes are you running with?
Okay, so the question is how many nodes we are running with Spark streaming. Isaac, do you want to answer the question?
Okay, so our data requirements haven't been that big. We have, the maximum we have used is 8 nodes at the same time, and that was able to process all of our data, all 5 billion per day. So
What was the size of an event? You said you had 5 billion.
each event is around 1 kilobyte.
How much time you were saying into one event was being processed? How much time it was taking for one event to process?
I mean, we can keep up in real time, so 24 over 5 billion.
So maybe one more question.
Okay.
Yeah.
There's one more. In your last slide, you mentioned the issue about the message loss. So is that the thing that you just don't need to solve, or just you're working on that?
Sorry, about?
In the last slide, the issues you mentioned for the structured streaming, there's one item is called the message loss. So do you have solution for that, or just it's not a problem for you?
Sorry, the data loss?
Yeah.
Precisely, our solution to that, you will never prevent data loss completely in a streaming application. I mean, it's part of the CAP theorem. But our solution to that is to run a batch job to ensure the consistency of the data afterwards.
Yeah. I want to add something to it that Kafka has notion of offset, like where the consumers are. Currently, Spark Stream, in the moment it pulls data from Kafka, right, would tell that I'm done consuming it. But I think going forward, I will try to work with the Spark community so that we expose APIs in Spark Streaming itself, so that it could commit once you're done processing and not when you just consume the data.
Yeah, but the thing is that if you try to retake from Kafka, there is a risk that, for example, message is processed correctly, but you somehow something failed, and then you try to retake from Kafka, and it will be processed two times faster. So it will be duplicate processing. So there is another risk. So do you have a similar kind of mechanism in the storm channel to guarantee that message is only processed once?
I think the message only process one. That semantic could be provided by Kafka, right? Kafka has the notion of where each consumer are, right? So if your pipeline takes care of reading a message, writing it, and then only then committing back to Kafka, that notion could be guaranteed. Yeah. Probably we could talk offline for more details. Yeah.
So let's thank the speakers
Yeah.
again.